Hello. All right, so we are going to start talking about how to use um, Adafruit IO service. Okay, so Adafruit IO, let's start here. Before we even talk about the board configuration, let's head over to io.adafruit.com, right? So that's the URL. If you don't have an account, which I assume you don't, you probably won't see this. You'll probably see something like, hey, create an account type of a prompt, and then so you'll create an account. It's free, right? So I'm on a free account using the Adafruit IO basic plan. We don't need to upgrade to anything higher than that, so we can just create a free account. And so what is Adafruit IO? Adafruit IO is a service by Adafruit, the company, the maker of a lot of these electronic components, including the Hazaf32 board that we've been using, right? So we've been sort of using their learning system to cross-reference different parameters of our ESP32 board. But besides creating electronics and hosting a variety of learning resources, they also have a service called IO. So here is the link, or just io.adafruit.com. So this service allows you to store data online, right? So you'll be able to capture data using your ESP32, and then you'll be able to store this data in the Adafruit IO service. This is fundamentally what makes an Internet of Things device, right? So it has to be internet connected and it has to be able to store and retrieve data. So we'll be looking at just storing the data. We'll retrieve the data using other services, but rest assured that you can do either with the board. So here's what we're going to do. So once you've created the account with Adafruit IO, we will create feeds. So you'll see here at the top, you'll have devices, feeds, dashboards, actions, and power-ups. So feeds is where we're going to be storing our data. So each feed, so let's head over to the feeds, click on this. Each feed will be able to store data related to one single sensor, right? So in this example, we will have a potentiometer and a photoresistor connected to our board. And so I will create the feed for each one of those. Okay, so we will be storing information separately from the potentiometer and separately from the photoresistor, right? You can, for your projects further on, you'll be able to use other sensors. What sensor that is doesn't matter. It's very much agnostic to the kind of data you're trying to send and the kind of device you're using, right? As long as you're complying with specific requirements that they're asking you to do, how to format the data, basically. So, so we'll create two new feeds, and then in order to comply with those requirements, we're going to have to install a library. So let's start with creating the feeds. I'll have one for potentiometer, and I'm just for simplicity, I'm going to call it knob, and I'm going to call it knob feed. There we go. And I'm going to create another one, call it photo feed. Photo feed. Okay. So this gives me two feeds on the Adafruit IO service. This will give me the abilities to store data from my sensors. Okay, so we have prepared the containers for the data. Now we need to execute the chain. So fundamentally, we will have the following components in the chain. We will have the sensors connected to the board. Then we will have the code that will read the data off of these sensors, that will connect us to the internet. And then once the board is connected to the internet, connect us technically authorizes to use the Adafruit IO service. And then once we're authorized and connected, it will be taking the data from the sensors and storing them regularly in these corresponding feeds. Okay, So the containers are prepared. Let's start in the beginning of the chain. I'm assuming that as you're watching this video, you're going to be pausing and sort of like creating services and downloading libraries as need be. So, so I'm going to try to follow more of a logical chain rather than the most sort of time efficient chain of events. So feel free to pause and like download, create accounts, and do all those things as needed. Okay. All right. So let's start then. Well, we already started. Next step is setting up the board. Okay. So we have the ESP32 right here, right? It's connected to our breadboard. And right now I have a potentiometer, right? Connected to three, with its three legs, connected to the three rows on the board. And so one of them will be connected to the power, one of them will be connected to the ground, and the other one will be connected to pin A2. Okay, so it is really important to know why we're connecting to A2 and not to A0 like we did before. Okay, so here's where I will briefly switch to the Adafruit IO pinout, and let's look at the description of the pins. So so let's head over to GPIO and analog pins, so general purpose input output and analog pins, right? And so right here you will be able to read the following information. So for example, for A0, this is an analog input A0 and also an analog output DAC2, right? So it can also be used as a digital pin, GPIO 26. It uses ADC2, analog to digital converter, right? So as an input, it's going to be taking analog information, meaning this variable voltage that comes up and down from the sensor, and it will be able to convert it to the digital information. That's why it uses an ADC. Okay, so Adafruit input A0 uses ADC2, input A1 uses ADC2, input A2 uses ADC1. It's not an output capable pin, but that's fine. We're using them as input, but more importantly, it uses a different ADC. So this is the reason why I switched to it. Instead of using A0, I used A2 and A3. Both of them are using the analog to digital converter number 1. And so if you scroll just a little bit further down, you'll see this notice. Note, you cannot read analog inputs on ADC2 once Wi-Fi has started, as it is shared with a Wi-Fi module. So ADC number 2 is used by the Wi-Fi module in order to connect to the internet, which means that inputs that are connected to the ADC2 or using ADC2, so input A0, input A1, and also input A5 are not going to be available if you're trying to connect your board to the internet, right? So therefore, we are going to be using inputs A2, A3, and A4. Okay, so in this case, since we only have two sensors, we're going to be using A2 and A3. That's why the switch. So please pay attention to this. This is really important. You will not be able to use A0, A1, or A5 if you're connecting to the internet through the Wi-Fi module. Okay, all right. So we have our potentiometer connected to A2, and we have our photoresistor. Now remember, photoresistor is a 2-pin sensor, as opposed to being a 3-pin sensor like a potentiometer, right? So 2-pin sensors require this pull-down resistor, right? The one that connects it to the ground rail right here. And then it's the same leg that connects to the pull-down resistor that will be connecting to A3. Okay, so this is the general schematic in this example, at least. you feel free to use other inputs, other sensors, other uh, configurations for the board, right? But ultimately, it doesn't matter, right? So all the components that you're going to be using are fundamentally going to be either 2-pin or 3-pin components. So for example, we looked at a button. A button is a 2-pin component, right? It requires a pull-down resistor. We looked at a temperature sensor. Temperature sensor is a 3-pin component. It has a voltage, a ground, and a sensor pin, and so on and so forth. So the vast majority of sensors will be either 2 or 3-pin sensors. So if you think about what kind of information to store, what kind of sensor to use, just remember that it's one of the two. You're going to be using either a 2-pin or a 3-pin configuration. And so here I'm using potentiometer and photoresistor in this example because each one is a representative of their respective category. All right, so hopefully by now you've been able to assemble the board, right? And you've been able to connect your sensors. So we are ready to start collecting information. So in order to do this, we're going to need to write some code. So we're not going to be writing this code from scratch. It's not going to be just an empty Arduino sketch that we're going to try to use, right? So here it is. We are going to be using an example from the library that we will install. Okay, so in order for us to properly connect to the Adafruit IO service, we will need to install a library. So head over to your library manager and Adafruit IO, I believe IO Arduino, something like this. Arduino. There we go. So Adafruit IO Arduino is the library. I don't know why it doesn't come up as the very top one, but so I believe right now the version is 4.3. If you're watching it at some point later, feel free to install the most recent version, but make sure Adafruit IO Arduino library is installed. So it is very possible that this library will also ask you if you want to install some additional libraries along with it. And while we're not going to be using those additional libraries, that might come handy. And so I recommend that when you're installing it, you just say yes, install those additional libraries. They're not going to take a lot of space on your hard drive, but at some point they might come handy. So just have them in. They've all been vetted and are guaranteed not to contain any kind of malicious code or anything like this, right? So install them, and then let's head over. So if you need to pause. But then once you're done, let's head over to the examples. So right here in the examples, I am going to scroll down and head down to the examples from custom libraries and Adafruit IO Arduino. So there are tons of really good examples on how to use Adafruit IO service right here. But we are going to head over to Adafruit IO 08 analog in. So let's open it up. We're going to be lifting components off of it. So this example is a part of a tutorial. So if you command click, or I believe control click if you're on Windows, on this link at the top of the example, it will take you here. This is the tutorial called Adafruit IO Basics, Analog Input, right? So exactly what we're doing. So we're going to be loosely following some of this, but a little warning, a little word of caution is that they are using, in this example, a board called Huzzah ESP3266, a slightly different board, not exactly the same that the one that we're using. So some of the pinouts are different, some of the capabilities are different, but if you keep this in mind, if you cautious about making sure that you're readapting these examples in this tutorial for your own board, it's actually quite useful. So let's look at the example. So first of all, one thing that you might notice in the very beginning is that it has two tabs, right? It has Adafruit IO 08 analog underscore in is the .ino file. That's our regular Arduino files. And then it has something called config.h. And config.h is a typical C-type language file. It's technically called a header file, therefore the extension H. And it contains some additional supplemental information about some of the components being used in your code. So we're going to need to create one of those too, because if you click on it, you will see that in this case, config.h contains the following information. First of all, information about your username and your authorization key for Adafruit IO, right? This is important. And then it will also contain the name of your Wi-Fi network and the name of your Wi-Fi password, okay? So, and then if you scroll a little bit down, there's going to be a little bit of code that will actually enable that connection. But let's start by filling all this out. So first, Adafruit IO config. If you look at the example, it says visit io.adafruit.com if you need to create an account or if you need your Adafruit IO key. So if you haven't created the account by now, please do so. Head over to io.adafruit.com right here. Hopefully you've done so and you've created the feeds that will eventually contain the information that we're going to send. And now as for the key, you will see this big yellow button right here with a key icon on it. That's going to be our API key. So if you click on it, you will see this, right? I don't mind showing you my key simply because I'm going to hit this regenerate button the moment I'm finished recording this video, right? So in this box, in this modal pop-up, you will see that there is information that's ready to be copied and pasted. So for example, for Arduino, you could just copy and paste these lines, right? And they're going to be very, very similar to the lines that we see in the example, except here they have some dummy information. So, all right, so let's head over, copy and paste this, but where? Let's create, so I think we forgot to create our own config file. So let's do that first, then we'll be doing our copying and pasting. Okay, so in order to create a new tab, you can click here in the corner, right underneath your serial monitor icon, to this three dots, and it will give you an option to add a new tab. Let's do config.h. Here we go. Now we can head over here and grab these lines for the username and the key for Adafruit IO service and start with that part. Okay, so this is going to be your IO username and IO key. Now, once we're done with this, following further through the example, we're going to need to define our network ID and our password for the network. So you can just copy this, paste this in here, and then hopefully you know all this information. I obviously would not be able to tell you what the password is, but if you're at some point wondering which network you're connected to, you can just head over, for example, into the Wi-Fi tab on a Macintosh, or in the similar information on a Windows computer and see which network you're connected to, right? So for me, my network is called AltCast and so this is what I'm going to be putting in here. So something like, and then put in the password, whatever your password is, right? So this is what is gonna start your config right here, right? And then we're gonna head down and start and continue copying and pasting from our example, okay? So, okay. So we are gonna next move on to this line, include Adafruit IO underscore Wi-Fi, right? That's gonna be the header file that's gonna bring in all the information about how to use the Wi-Fi module on the ESP32 board with Adafruit IO. Okay, so once we're done that, there's this fairly long if and if whatever else and if statement definition that basically kind of helps you define different boards, right? We don't really need this. For the board that we're using, we're not going to need this. Even though you might see here that says configure the pins used for the ESP32 connection, we actually don't because we're not going to be doing some more advanced stuff that, for example, will let you use the ADC2 and so on and so forth. So really, we just need this one last line, the line that's line 52, right? The one that says Adafruit IO Wi-Fi IO, right? That's the function. And then connect, right? So this is going to be username, key, Wi-Fi, SSID, and Wi-Fi password. So this is basically a function that will create the connection to Adafruit IO service through the Wi-Fi network, right? So it'll connect to your Wi-Fi, connect you to the internet, and then authorize you for use with Adafruit IO. Okay, so that's that. If you scroll further down, you will see there are some examples for additional other boards and like things that use connections that are different, like for example, Ethernet connection and so on and so forth. But we're done. We are done with our config file. Okay, so we can head back over to Sketch in both places in our own code example and in the example that we're following. And so the next order of business for us is now to just include config.h into our main code, right? So that everything that we've done in the config file will also be executed as a part of our sketch. All right, so following further down the example, you will see that they are defining their pins. So we can do the same thing. We can define our photocell pin, and let's define, actually, I'm gonna do it in a different order. I'm gonna define a potentiometer pin. And so they're using a 0 because the board that they're using would allow them to. We can't, and we have to remember to configure our inputs correctly. So for us, it's going to be A2 and A3. If you remember, this is how our sensors are connected. Our potentiometer is connected to A2, and our photocell is connected to A3. Okay. All right, so we have our cells defined. And then they're going to be doing this like current and loss thing where they're like checking if the values are corresponding. We don't need to get into this. We're actually going to make code that's a little bit simpler, but I'll explain why they're using this current and loss once the time comes for us to get into that part. So after that, you have this set up the analog feed. We don't have any analog feeds. The feeds that we have are knob feed and photo feed, right? So those are the feeds that we're going to be setting up, but we can still follow the example from here. So if you notice, what they're doing is they're saying Adafruit IO, and feel free to just copy and paste from there, feed, and then asterisk. Asterisk is important. I'm going to call it like this, full pot feed camel case, right? So this asterisk is important. It's one of those peculiarities of a C-type languages like C and C++. It basically means that it's a pointer. It's not a variable that holds a value. It's a variable that holds the address of the memory location where the value is stored. It is important because those are low-level languages, and therefore they are concerned with memory management for the computer. But for most users, that just simply means an unnecessary complication. Including for us, we would typically not even bother with something like this on a higher level programming language like Python or Java, but with C-type languages, we do have to because that's what they do. So, but just remember to add this asterisk there before the name of your pod feed, and then we are going to add io.analog, and then that's what am I saying? io.feed, and then that's going to be our. I'm just going to copy and paste, right? Knob feed for the potentiometer, and then I'm going to do the same exact thing. Copy and paste this line, and then this is going to be photo feed, and then copy and paste the name of the feed right here. Okay, don't rely on my spelling at all, and I recommend that you don't rely on yours either. Just copy and paste as much as you can. All right, so that's it. That's the setup, right? We have the potentiometer pin, photocell pin, and then we've set up our feeds, and we set up our connection. So now in the setup function, we're gonna need to start our serial connection and actually execute our Wi-Fi connection. So we can follow the example. There's some really neat tricks that they're using. So for example, if you copy this line, serial.begin, they're using a slightly faster, well, significantly faster baud rate. So before we have done 9600 baud rate. If you want to stay with 9600, doesn't matter. But if you're going to be using 115200 baud rate, make sure that when you're using your serial monitor, right here, you will have an option to change the baud rate for your connection. You will have to change it to match whatever baud rate you're using. Otherwise, your serial monitor is not going to work. So keep an eye on that. And then another, so the neat trick that they're using right here, right on the next line. So let's copy and paste another line from their code. So while not serial. So while is a type of loop, right? So we've seen for loops so far, right? And whereas for loops will execute a given number of times until a certain condition is met, while loops execute for as long as a certain condition remains in a certain state, right? So for example, is true or false. It's slightly different semantic approach, and honestly, like I didn't feel the need to go too far into while loops because for the most part, you can do everything that they do with just for loop, just slightly differently formatted. But in this case, so what's happening here is they're saying while this condition is true, and this condition is defined as not serial. And so fundamentally, this is checking for what's known as a truthy value, the value that one way or another will execute for something like, or evaluate to something like true or one or yes or defined or something, right? And so basically what they're saying is while we don't have a true serial connection, right? A serial connection that somehow evaluates as true, we're going to do something. And what are we going to do? Typically, you would have like curly brackets here, and you would say like, oh, you know, do this, right? But what they're doing is saying, while we don't have a serial connection, just do nothing. Sit and wait until we do establish our serial connection. I find it kind of neat, so I just thought I'd bring your attention to this. Anyway, so once we don't have, for as long as we don't have it, we're going to sit and wait. But once we do, we are going to print into the serial connection the following statement. Serial.print connecting to Adafruit IO. So you can go ahead and just put this in, right? So it's going to print the following sentence into the serial connection, right? And then we can call the function that actually will execute it, right? io.connect. Right, so IO, if you remember, is that this IO, right? That's what we've set up. That's the object that we've set up. That's the Wi-Fi connection, and it's going to do the connect. All right, so we're going to do the connect thing, and it's going to do its own connecty stuff, the code that's written in the library that we brought in, right? And so here is the sort of while we're waiting, so you can copy and paste this entire while loop, and paste it right next to the IO.connect. So while the connection status, while the IO.status is less than IO connected. So IO connected is defined in the library, and it's probably defined just like we're defining this here as some number. And my guess is maybe it's number 1 or number 2 or something like this, right? So some kind of an integer. And so the IO.status function will return a number, but it's going to be either a negative number or a 0 if you're not connected. And so negative number or a 0 is going to be less than 1 or some other integer that is defined here. So this is what we're saying. Basically, as long as the connection status comes in as something lower or less than IO connected, we are going to print a dot into the serial port and wait for half a second, 500 milliseconds, right? So 500 milliseconds is half a second. We're going to put the dot in the serial monitor and wait, and then put another dot and wait, and put another dot and wait, and it's going to be a row of dots for however long it takes us to actually connect to the service. So hopefully it's not going to take too long, but this is some kind of user feedback, right? Informing the users of the system status. What is happening with the system while they're waiting for things to start working? Okay, very useful. So the next thing we're going to do, we're going to serial.println, right? And we're just going to do a simple println statement, right? That's going to insert a new line character, so kind of like an empty line in our serial port. And then we can print out the status text. That's the piece of text that this IO object will return for us, informing us on what is the status of the connection. Right, most likely it's going to be a statement. Basically, you've been connected to Adafruit IO service. You can now do the thing that you want to do. All right, so that's that. That takes care of our connection, right? And then we do move on to the loop, right? And the very first thing that you need to do in the loop, you'll see that there is like a big warning statement about this. IO.run is required for all sketches. It should always be present at the top of your loop function. It keeps the client connected to io.adafruit.com and processes any incoming data. This is really important for you to execute this function at the very beginning of your loop statement. So we're going to do that. We're going to say io.run. It's going to keep that connection running and active. Okay. Next order of business, we are going to create two values and store our sensor data in those values. Okay, so for example, here they have a current value and they read the read the value of the photo cell and store it there, right? We can do it in a simpler way. We can just create those variables here. We can say float. Let's do pot value, and that's going to be analog read, right? And analog read from the potentiometer pin. Copy, paste, and then float photo value, same analog read photo cell pin. Don't forget the semicolons at the end, and so this should give us our values. So next in the example, they're comparing the current value with the last value, and if it's the same, they hit return. So they don't execute anything else in the loop function. They return back out of the loop into the very beginning. Why are they doing this? What's the point of this? The reason why they're doing this is a data restriction in the Adafruit IO service. So if you head over to Adafruit IO and hit their API documentation right here, it's going to be at the very bottom in the footer in the Get Help Quick Guides API documentation. So clicking on this will take you to the documentation that will describe basically the entire functionality of the service. and it includes the examples in basic command line, examples for Arduino and Python and Ruby programming languages. But for us, the important thing is to hit this rate limiting page right there and take a look at the following statement. If you have a free Adafruit IO account, the rate limit is 30 data points per minute. That means that you cannot store more than 30 values within 1 minute. And that's an average, obviously, but if you're storing information from one sensor, that means that you can only store the value about once in 2 seconds. Okay? So the loop typically runs way faster than this. It runs probably 100 times a second or so, right? So you need to figure out how to limit the amount of data that you're sending to Adafruit IO service. And so this is what they're doing here in this example. They're limiting their own amount. If the value hasn't changed, we're not going to do anything, right? This rate limiting is extremely important because if you're going to start bombarding the Adafruit IO service with unrestricted, unlimited data, they will shut down the service. You will very quickly get a warning on your feed saying you're exceeding your data rate, and literally within about a minute or two, you'll get a suspension, right? If you continue trying to do so, meaning if your board is still connecting and still bombarding, your account might get suspended. You might have to create a new account. So it's really important that we don't try to overload the service with all the values, and we respect their restrictions. So I'll show you another way of doing this, and that's the way that we are going to be using. We don't have to do it this way, and I think there is a simpler way, but we will definitely keep an eye on this rate limit and make sure that we're not overloading the service. Okay, let's continue through the example. So next thing we see is serial.print sending, and then they're printing the value that they're sending, and then they have analog, this arrow thingy, and then save current. Okay, so analog, if you remember, it refers to the name of the analog feed. Okay, so our names of the feed are different, but the framework is exactly the same. So we are going to say serial dot print, right? So not println, because I don't want to insert a new line character, and then say something like sending 10 right? Sending potentiometer, and then serial dot print ln this time, and then the pot value. Okay. Notice that I added a space here after the column because I want the space between the column and my value, and there's no other way for me to implement that space. So once we've done that, we can say, let's grab the name of our pod feed, and then we do this arrow, right? It just simply dash and then greater than sign. And that basically is somewhat similar. It invokes a static method in, well, it invokes a method in the pointer. But again, let's avoid these complications. Let's just lift this off of the example and just know that this is how we're supposed to call our save method with the pot value. Okay, so we've done it with the pot value, and we can do the same thing with the photoresistor, right? So we're going to say photoresistor, and then instead of saving the pot value, we're going to be saving the photo value. And then this should say value, not value, but val, right? So this is where copying and pasting is important. If you notice that in some places I have it listed as photocell and in others I'm calling it a photoresistor, those names are entirely interchangeable. They refer to the same component. Some people call it one way, some people call it the other way. I lifted the name photocell pin off of the example. I prefer calling it a photoresistor, but fundamentally doesn't matter. But, so here's the important thing. We need to wait for a little bit, and you will see this explanation here. Wait 3 seconds because there are no active subscription. We can use delay instead of tracking mail, blah, 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 blah. So the reason why we're waiting is to specifically allow for a limiter on the amount of data or the number of data points that we're sending. So if we have two values, that means that in order for us to record them accurately and not overstep our limits, we need to send them call these two commands 15 times 15 times a minute or less, right? So therefore, what I'm going to do, I am going to introduce a delay of 5,000 milliseconds, right? So 60 divided by 5 is 12. So I'm going to be sending 12 values per minute, which is below 15, which is good enough for me. That means that I'm not going to be overstepping my limits, and I'm not going to have any problem with executing this code. All right, so this is how it's supposed to run. So save this, connect this to your board, right? Let's make sure that you are connecting to the correct board. Verify right here, upload, and once you've uploaded, make sure you open the serial monitor and you will witness the board connecting to the Wi-Fi, and you will witness the board connecting to the Adafruit IO service, right? So here we go. And then hopefully you will start seeing these messages, sending potentiometer, sending photoresistor, sending potentiometer, sending photoresistor with regularity. Okay, so now heading over to io.feeds, you should be able to click into your knob feed right here and see the results of your data. All right, so once you head over to the feed, once you click on it, you should be able to see this. You have values that were saved at a particular time. So you'll have a list of them, right? The time when the values were added, the value that has been created and stored, and then the location if you're enabling this feature or not enabling this feature. It doesn't matter for us really where we're saving them from. But this is where your information is going to be stored, and we're going to come back to this place when it comes the time for us to access this information from another program. We're going to be using P5JS, and we're going to be grabbing data from that feed. So for now, the important thing is that you have your boards gathering information from the potentiometer, from photoresistor, from whatever other sensor you decide to use and connect to your boards, right? That your boards are then connecting to Wi-Fi and connecting to Adafruit IO, and then finally that you're able to click into your feeds and look at the data being stored and verify that it's also happening in the serial monitor. Okay, so if you're having issues with your Wi-Fi connection, double check the name of your network and double check your password, right? If you're having issues connecting to Adafruit IO, make sure your name and IO key are correctly configured. Make sure your library is properly installed, right? Make sure that you actually have these examples, like the example that I've been using, because these examples come with the library that we just installed, right? So this one sure way to ensure to verify that your library is installed properly is to use these examples, open them up and see what's happening, right? And then finally, make sure that you're actually calling the correct code. If you're still having any issues connecting, we'll be able to troubleshoot them next time we meet in class. But this is it for now. Hopefully this is helpful. Reach out if you have any questions.